In this video, we'll explore media stream architecture and the specifics of organizing group conferences with 10 or more participants. First, we'll get acquainted with WebRTC, the technology for real-time audio and video transmission. We'll explain why a NAT mechanism is needed and how stun and turn servers ensure a stable connection between clients. Finally, we'll compare the architectural models P2P, SFU, and MCU, highlighting their advantages and limitations. One of the most popular and widely used technologies for media streaming is WebRTC, a standard that enables real-time audio and video between browsers and apps without requiring separate media servers. A prominent example of WebRTC in action is Google Meet. Essentially, WebRTC was originally designed for peer-to-peer connections. It establishes a direct connection between two devices, allowing them to send and receive streams directly, without an intermediary server. This makes it ideal for one-on-one video calls. However, to implement this mechanism, a server is still needed, because initially, none of the devices know where to send the data. Such a server can be, for example, a Node.js application using WebSockets, which facilitates the exchange of information between clients, including their addresses, to establish a direct peer-to-peer connection. First, user A sends a request to the server, proposing a connection to user B. User B can then accept the proposal, after which they start exchanging ICE candidates. An ICE candidate is an address that devices can use to establish a direct connection with each other. Each device usually has multiple candidates. For example, if two devices are on the same local network, they can simply exchange local addresses and communicate directly. However, if the devices are on different networks, the packets cannot reach each other via local IPs, because routers on the internet don't know where to send them. Your local IP address is never directly routed on the internet. Instead, every time you go outside your local network, the NAT mechanism kicks in, replacing the local IP with a public one. NAT operates inside a router or gateway and keeps a mapping table to know which internal device should receive the response once it comes back. You might wonder, why do we even need local and public addresses? Why not make all addresses public? There are three main reasons. Exhaustion. IPv4 provides roughly 4 billion addresses, which is not enough for all devices worldwide. Security. If all IPs were public, every device would be directly accessible from the internet. Local IPs, combined with NAT, hide devices and act as a basic firewall. Flexibility and scalability. Home and office networks can use any private address ranges without conflicts. Here's the challenge. You cannot just ask your router for your public IP. To pass it to WebRTC, you first need to send data to a third-party server, which responds with your device's public IP. You might think you can do this via your own server. Theoretically, yes. You could create a route that returns your public IP and feed it to WebRTC as an ICE candidate. However, NAT only ensures delivery while the TCP connection exists, and it does not guarantee that the same public IP can be used for ongoing communication later. Simply put, you go to your server, request your device's public IP, and send it to another user. That user might be able to connect for a short time, but eventually, the IP becomes unreachable, and packets stop arriving. Theoretically, you could handle this by requesting an updated public IP again from your server. But since most apps run over TCP, this can take 1 or 2 seconds, and nobody likes such long pauses in a live call. If you haven't yet grasped the problem with TCP, we'll compare it with UDP, which is the protocol WebRTC mostly uses. Before receiving a response over TCP, you first need to establish a connection, which requires 3 additional steps. First, the client requests a connection. Then, the server confirms readiness. And finally, the client acknowledges that it has received the response. Only after the connection is established can packets be sent and received. With UDP, there's no need to establish a connection. Packets can be sent immediately. There are other differences between these protocols, but the main reason WebRTC uses UDP is for low latency. TCP and UDP are not compatible, If your server runs on TCP, you cannot simply configure it to work over UDP. To ensure low latency in WebRTC, you need a specialized stun server running on UDP, which allows clients to quickly determine their public IP address. For testing, you can use Google's public stun servers, which allow you to verify connection functionality. In production, however, you need to either deploy your own stun server or use paid solutions from cloud providers. In practice, a single stun server is often not enough. Sometimes, two devices may try to initiate a connection, but due to strict NAT settings, neither can receive incoming traffic. In such cases, you need an additional turn server, which accepts packets from both clients and relays them between them. Neither device needs to accept incoming traffic. They simply send packets to the turn server and wait for responses. This approach bypasses NAT restrictions and ensures stable data transmission in any network conditions. The turn server also solves another problem. When clients are behind carrier-grade NAT, where a single public IP is shared by thousands of devices, the turn server keeps a session table that allows it to accurately determine which client to forward packets to. However, for group calls, this is still not enough. As we mentioned earlier, WebRTC was initially designed for peer-to-peer connections, where communication happens between two participants. If you want to implement a conference with more participants, you would need to connect everyone to everyone. In practice, this works well for a maximum of 6 participants. To achieve high-quality media streaming among a larger number of participants, you need an improved architecture. Before explaining it, we want to remind you that our team is open to new proposals. If you or your business need an online solution, we are happy to provide a free consultation and suggest the best cases for implementing your product. So, if you plan to use WebRTC on a standard architecture, you will face issues with the number of active connections and high CPU load. In fact, for each pair of participants, a connection must be established, which includes 2 channels, one for sending data and one for receiving data. Accordingly, with 4 active participants, you end up with 12 connections, each with 2 channels, totaling 24 streams. If the number of participants reaches 10, you get 90 streams. In this case, synchronized playback is nearly impossible, and CPU load will be very high. To solve this problem, 2 architectural approaches were developed: SFU and MCU. In SFU architecture, instead of sending each participant's outgoing stream to every other participant, you send your stream to a central server, which then forwards it to all other participants. The number of incoming streams still increases, but each participant sends only one outgoing stream. This reduces the total number of streams to 55, significantly lowering client load. This approach is very popular and widely used by companies and engineers. There is a more advanced approach called MCU. This mechanism not only forwards streams, but also mixes them into one, reducing the total number of streams to 20. However, a major disadvantage of this approach is the need for very powerful server infrastructure and significant implementation costs. In summary, for implementing a high-quality group connection, you will need 2 additional servers, stun and turn, as well as 1 dedicated server using SFU or MCU architecture if you plan to run group conferences.